Today we are going to discuss about the sampling theory and why sampling is necessary in order to extract the desired message signal from at the receiving side. So we know that most of the signal in the real world are continuous. So if the signals are continuous, uh, so we have to convert them into the discrete time signal because most of the electronics are digital components, so they understand the digital signals. So that is why you have to convert the continuous signal into the digital signals. So to convert the continuous signal into digital signal, you have to learn about the sampling theory. So sampling theory, so we will discuss the sampling theory today. So what is the sampling theory? It is a process of converting the continuous signal into discrete signals. So that is the proper definition of the sampling theory. But for proper reconstruction at the receiving side, the continuous signal sample must be sufficient. It means that you have to sample the signals like, so suppose if your signal is something like that, so you can do sampling, so like this, like this, like this. It means that you have maximum 4 samples, but maybe you can increase the number of sampling, so like this, like this, like this. So you see, so if you increase the number of samples, then you can have a smooth reconstructions. You can do the reconstruction for a less number of samples, but there are more, you can lose some proper information. So number of samples depend on the maximum frequency of the signal. So sampling can be 3 types. The types of the sampling, it can be ideal, it can be natural, and it can be flat top. So what is the statement of the sampling? A band limited signal having finite energy which has no frequency components higher than fm hertz is completely described by its sample value at uniform interval less than or equals to 1 over 2 fm. So it means that the time interval ts, so if I want to define ts, so time between these two intervals, so that is ts. So ts should be much less than 1 over 2 fm. So this is the definition in terms of time duration. So in terms of the frequency, we can define the same statement in another way. A band limited signal having finite energy which has no frequency component higher than fm may be completely recovered from the knowledge of its sample taken at the rate of 2 fm sample per second. So in that case, your sampling frequency should be equal to or greater than twice the modulating frequency. So like you can see, so if you are doing sampling like this, so the duration from here to there is ts for this case. So let's understand more by taking some examples. So if you have a signal, so that is a band limited signal to fm, you can write the signal in terms of time domain. So like this is your continuous signal, and so x-axis is time axis, and this is the amplitude of the signal. So if you want to write the same signal in term in the frequency domain, so how can you write? So for this, so this is the condition that omega should be much bigger than omega m. So you can write the same signal in frequency domain. So the x of omega, and this is the negative component, and that is the positive component, and this is the modulating frequency. So in order to do the sampling, you need to have a pulse train. So how can you represent pulse train? So this is the pulse train, so a constant amplitude, and then you have a different pulses at a different time interval. Like at 0 you have this one, at ts is this one, 2 ts that one, 3 ts that one. So this is continuous. Similarly on the negative side, so minus ts, minus 2 ts, minus 3 ts. So you can represent this term by delta tst. So mathematically, if you want to represent this mathematically, so you can write these equations. Delta ts is equal to 1 divided by ts multiplied by 1 plus 2 cos omega st. So omega st is the sampling frequency, plus 2 cos 2 omega st plus 2 cos 3 omega st plus so on. So this is a continuous. So you need a multiplier. So you multiply the pulse train with the continuous signal in order to get the sample. So you multiply the pulse train with the continuous signal, and then you will end up with GT. So GT is the product of your continuous signal and the pulse train. So mathematically you can write x of t multiplied by the pulse train. So if you want to write in term of graph, so that was your continuous signal. So these are the pulses. So you can see, so you can represent your pulses. So these are the samples. So these are the sample values, and this is the sample value at each continuous amplitude of the signal. So if you wanna write this equation mathematically in the frequency domain, so you can write in the frequency domain g of omega is equals to 1 over ts x omega. So this is the frequency domain. We know x omega plus x omega minus omega s plus x omega plus omega s means upper sideband, lower sideband, plus x omega minus 2 s omega s plus x omega plus 2 omega s, and then so on. And the rule for that one is omega should be much bigger than 2 omega m. And graphically we can represent this like these are the pulses. So this is the graph of omega x, and this is the graph of omega minus omega x. Like this one will be omega plus omega x, this one will be omega, like you can write this one is omega plus omega s, and this one will be omega s minus omega. Okay, so omega minus omega s, and then so on. So similarly on the negative side and similarly on the positive side. So but you want to recover the message. So it means that if you want to recover the message, so you have to use the low pass filter whose cutoff frequency is omega m. So if you use low pass filter, you know the separation between these graph is very high, so you can easily extract the message signal from this pulse, and the remaining are blocked by the low pass filter. But for this you need to consider a few conditions, like as long as fs should be much bigger than 2 fm, then GW will repeat periodically without overlapping. You can see there is no overlapping between these two, there is a quite well separation between these two. So spectrum of GW extends up to infinity, like it is extending up to infinity on both sides, but our purpose is to extract omega of x, like you wanna extract the omega of x. So in order to extract the omega of x, you can use the low pass filter whose frequency is omega m. So there can be three cases, like the first case, the sampling frequency should be greater than or equals to 2 fm. So it means that if this is the case, you can easily extract the message signal. There will be no overlapping between these two graphs. The second case is fs is equals to 2 fm. So this is also known as a Nyquist criteria. In this case again there will be no overlapping, but they might touch each other. So like this. So there will be again no overlapping, and then using the low pass filter you can still extract the message signal. The third one is the sampling frequency less than 2 fm. So this is the undersampling. So it means that now your sample is overlapping, like here. So you see, like here, and then like. So you see, so this is the case. So it means that this is region of overlapping. So if this is overlapping, you cannot construct your message. So I hope you understand the basic sampling theory today. So in our next lecture, we will again try to explain all these three cases that we have mentioned, so that you can completely understand the sampling theory. So if you have any question, you are most welcome. You can ask the question and write in the comment box. We will try our best to answer the question. Thank you for watching the video.